Hello, my name is Colin Ngo, and I'm from Section C of Physics 2211, and today I'll be talking about Lab 2, Projectile Motion. The purpose of this lab was to observe, analyze, and compare the projectile motion of an object using computational models considering gravity and drag force. Just quickly here, the results preview. The findings saw that our computational model that did not account for drag had significant differences with our observed data. However, our model with drag accounted for was more similar. However, there were still some differences due to errors that we'll discuss later. Here we have our data that's graphed. Our orange line here is our predicted computational model without drag. This blue line here is our observed data, and the green line right here is our model accounting for drag. Just to introduce our fundamental physics concepts and principles, we have non-constant velocity for this lab due to a force, momentum principle, which will apply to find our derived equations, gravitational force, which causes that non-constant velocity, as well as drag and air resistance. So we'll just start off with Newton's second law, F net equals mass times acceleration. We'll apply the momentum principle to get this derived equation here, which is the velocity update formula. And along with that, we'll also get the position update formula, and we'll use this iteratively due to the fact that velocity is non-constant. And that non-constant velocity is due to the fact that we have gravitational force, Fg equals mass times g. And then we also have our drag force here, which is our proportionally constant times the speed squared times the unit vector of velocity. Now, lab setup here, we have our initial conditions, which I'll discuss later. Our materials, which was a paper ball, a ruler, and our camera. Our system was the paper ball, and the surrounding was the earth, and everything else, basically. Our units were meters, seconds, and kilograms. And our axis orientation here, we put the origin under the initial position, our x-axis on the floor, and on the right side was our positive, and up was also positive. This is another diagram, our paper ball and our ruler, and this is our experiment in video. Now, as mentioned before, this is our data graphed. We have all three lines here, and as you can see, our predicted computational model without drag overshoots our other two lines by quite a bit. However, when we include drag in a predictive model, we can see that it's more similar to our observed data and a bit more accurate when predicting trajectory. However, there's still some variation, and that's due to some error. And I'd like to point out as well that our observed data has a higher peak than both our computational models, which is also due to some error. Here we have our computational model and its initial conditions. We have a object mass of 0.0048 kilograms. We have our initial position, which is about a meter high, and then we also have our initial velocities in the x direction, 1.521 meters per second, and then 1.30 for our vertical velocity. Our start time is t equals 0, and our delta t is 0.033 due to our time step. Here we have our loop. This loop is used for both the drag and non-drag computational model. The only difference would be our b value here. So for not drag, we would set this equal to 0. We have g equal to 9.8. We have our end time in our while loop. We have our drag equation here, and we use the mag and norm function to find the magnitude and the unit vector respectively. We also have our gravity here as a vector, and then we add these two forces up to get net force. And then we also include our velocity update equation and our position update equation, which updates iteratively through our while loop. Then for the drag, we set this b value to a non-zero number, which is 0.0012 in this case, and we found this experimentally. So here, the model without drag, we outputted two visuals here, our trajectory right here on the right, as well as this diagram where we have our velocity arrow and then our gravity arrow pointing downward. And then with drag, we have the addition of the drag arrow, which is opposite of velocity and opposite of the motion of the object, and then we also have this trajectory outputted to the right here as well. So without drag, the sources of error would be air resistance and then position tracking, which is just human error in using the software. And then with drag, we also have the position error tracking as well as experimental B, and due to the fact that we found it experimentally, there is some margin of error that could have affected our graphs. For human error, we want to capitalize on the fact that there's camera movement and camera orientation, which could have impacted the data as well. So, terminal velocity, what does it mean? It's when net force equals 0, and in this case, we could not find the terminal velocity due to the fact that our experiment was too short. However, through the computational model, we can show our terminal velocity here by just extending our while loop to 2.5 seconds, and in that case, we get a terminal velocity about negative 6.25 meters per second. So to find the terminal velocity, we would just need to extend the experiment time and go from a higher height. In terms of this what-if situation where we throw a ball directly up using speed, to the same initial speed, sorry, this will take a longer time due to the fact that a full initial speed will just be the y component, And so if we look at these two equations here derived from the kinematic equations, we can see that for t up, it's equal to 2 times speed divided by g, and this would be the same thing. However, it's going to be a component of the speed, and so it's going to be a lesser time than when we throw it directly up. So to conclude, we had two models, one without drag and one with drag, to compare a projectile motion of an object, and we saw that our drag model was significantly more accurate than our non-drag model.